Great, thank you. Well, welcome everyone. My name is Wes Hines. I'm the nuclear engineering department head here at the University of Tennessee. We're broadcasting today through Zoom, so I'm in my office here. We've been lucky to have our last few webcasts in our new building too, so I think we're all still excited to be in our new building. So we're very lucky today that, and sometimes these Zooms make more sense when we have distinguished speakers that can't make it here to campus. It allows us to reach out and really get some new views and some different types of speakers. So today we have Professor Anil Prinja. He's currently a distinguished professor of nuclear engineering at the University of New Mexico and was founding chair of the department from 2014 to 2019, having previously served as the associate chair from 2002 to 14, when that was in the Department of Chemical and Nuclear Engineering at University of New Mexico. And I was privileged to be invited to serve on their board of advisors for several years. So I got to learn a lot about New Mexico and a lot about Professor Prinja. He obtained his Bachelor of Science, his PhD in nuclear engineering from Queen Mary College, University of London, UK. And he was a research faculty in nuclear engineering at UCLA from 80 to 87 prior to joining New Mexico in 87. He's primarily a theoretician, that's hard word, Anil. A theoretician with research interests in investigating stochastic neutron populations in various nuclear security applications, radiation transport and stochastically mixed materials, high energy charged particle transport, and uncertainty quantification. He's also a fellow of the American Nuclear Society way back in 2003. So welcome.
Thank you, Wes, and thank you, Jason. If he's on the seminars, he extended the original invitation.
Yeah,
really.
Oh, there he is. Hey, Jason.
Really thrilled to be giving this presentation. I'm sorry I'm not there in person, but maybe in a few. At least in the near future, maybe as we all start to travel more, we'll change all of that. I would have enjoyed talking to the faculty, meeting and talking to the students and the faculty of the department. And congratulations on your new building. Just looking at Wes's office, that looks fabulous. The view looks great. But that's maybe because you're the chair. You get the best office in the building.
No, I don't have the best office. No, Dr. Coble down there, and she has a better office than me.
Okay, so I should share my screen and let's see if we can make this thing work. Let's see, that's the one, so share. How's that? If I go to full screen mode, does that work?
That works.
That works, good. So I'll be talking to you today about stochastic modeling of neutron multiplicity distributions, and you'll see why the relevance of the word that Wes was struggling to pronounce as we progress through the talk. Right off the bat, I want to acknowledge the support of our research sponsor here, that's NNSA. It's through the Consortium for Monitoring Technology and Verification, MTV, that's led by the University of Michigan, and the director of which is Dr. Sarah Pozzi. As is always the case when professors make a presentation, the work is always done by the student, and we just get to talk about it. And then it's no different in this case. Very pleased to have an outstanding student working with me. He's the graduate MTV fellow that's supported on this grant, and that's Jawad Musa. Let's see. So why stochastic populations? What's the interest there? Stochastic populations or stochastic behavior arises anytime you have a nuclear assembly, i.e. a multiplying medium that has some sort of random source in it. Typically in power reactors especially, we try to minimize the amount of stochasticity. We suppress it by making sure that there are strong sources and we control it. And so, however, there are many situations in which strongly stochastic regimes are encountered. And the stochasticity is inherent, is an inherent nature, part of this, of our application. Neutrons are discrete point particles. They transport in media with randomly distributed other point particles, which are nuclei, and the interactions with the nuclei are probabilistic in nature, capture, scattering, and fission. All of that leads to a fundamentally stochastic problem. So anytime you have a multiplying system, but with just a weak source of neutrons internally, in this case spontaneous fission, you are going to have a strongly stochastic regime. So that creates a dichotomy. On the one hand, the stochasticity creates a potential for hazardous conditions, criticality safety events that are possible in spent fuel storage, during reprocessing, and recriticality of molten cores. Pre-initiation phenomena in burst reactors that we're all familiar with, and also nuclear weapon safety. The stochasticity in all of these applications is a very dangerous situation. On the other hand, strong fluctuations of the neutron population from the mean are actually an opportunity. They are a unique, any fluctuations are a unique indicator of the presence of special nuclear material. And so these fluctuations, if we can measure them or quantify them, can be used as can be thought of as stochastic neutron signatures to actually fingerprint these special nuclear material. So this process of what's called passive detection, identification, and characterization of nuclear materials is a central goal in nuclear safeguards and non-proliferation R&D, trying to defeat the specter of nuclear terrorism. So let's look at the origin of stochastic behavior. Where is it all? Well, the spontaneous fission and subsequent generations of induced fission that the neutrons cause are central in the emergence of stochastic populations. So here we have a single neutron chain. A neutron chain, which I'll be using the terminology a lot, is some initial neutron and all of its subsequent progeny. So a neutron collides, causes fission, produces more neutrons, and some of those neutrons are absorbed, others are leaked, and others cause further fission, and the neutron population can grow or die depending on the amount of material that's there. The key thing we need to note in fission is that the number of neutrons emitted in fission is a random quantity. We are used to thinking of the number of neutrons as somewhere between 2 and 3, and we say 2.5 in all our reactor applications. In reality, the distribution is much broader. You can have anywhere near between 0 and 10 neutrons emitted in either spontaneous fission or induced fission, and interestingly, the number of photons that are emitted is much larger. Can be much larger. It's a much broader distribution of. So the blue line here is spontaneous fission distribution.
So Anil, let me stop you for just 1 second. The slides aren't advancing on our side.
Oh, where are you? Are
yeah,
you on
so
the title?
Yes, it's still on the title slide as far as we can see. So you started referring to a plot that we can't see.
So is this going to be better then?
Yes, we can see. I can see it advancing now.
So I see the problem is when I went to full screen, I couldn't. I can't. So shall I leave it here? Does this work?
Yes, we can see it now. Yes.
So maybe I can just do that. Hopefully that's better. Sorry.
That works. That works.
Okay. Well, I'm sorry. You should have stopped me earlier. This was my introduction, the reference. So this is the plot, right? So this is a neutron chain causing fission through, the fission process through a sample, and these are what we call the fission neutron and gamma multiplicity distribution, right? It's this statistical spread when you have only weak neutron sources. In such a spontaneous fission in a multiplying medium, is that we're going to see stochastic behavior of the population. So here's an example. So if you consider a single burst of neutrons from a spontaneous fission event and look at the probability of there being n neutrons in a sample of varying, an S&M sample of varying mass, you get a plot like this. So this is the probability distribution. This blue line over here is the original spontaneous fission distribution, right? Anywhere between 0 and about 8 to 10 neutrons. But in the black line over here, you see the effect of multiplication, the induced fission. So when we have a sample of 335 grams of this mixed 80 weight% 239, 20 weight% 240, and 240 is plutonium-240 is the element that has the that provides most of the spontaneous fission neutrons. And you can see how the tail starts picking up, that you start seeing larger and larger number of neutrons. Okay, there's nothing Gaussian about this distribution, so you trying to characterize this with a mean won't work. But the important point is, though, there is this tail that's very distinct, is very unique, and if you can measure that, you can detect material. So the object, one of the goals is for computational or theoretical work is to be able to compute distributions like this under very general conditions. So what are some common characteristics of stochastic populations? Sorry, Jason, is my slides advancing now?
Yes, they are.
Okay. So we have what I call weakly overlapping neutron chains. So each spontaneous fission, a neutron creates a fission, then other neutrons create other fissions, and so on. These successive chains that are spawned by different spontaneous fission events, when they are well separated in time, i.e., because the source is weak, then you're going to get the neutron population. The neutrons from each spontaneous fission event don't overlap much, and you're not going to get a fluctuating population. So you see potentially large fluctuations in the neutron population. You can have the population become extinct at certain times, and if you're in a supercritical system, a single neutron can drive a chain to divergence. It can grow without bound. Most importantly, in a stochastic regime, the mean neutron number is not representative of the actual neutron number at all. We need more additional stochastic information. Here's an example of a simulation of a burst reactor. And so in the blue line over here is the mean, the red line, the wiggly red lines over here, the fluctuating red lines give you the actual neutron population in a particular instant. And as you can see, it initially will fluctuate a lot, and then eventually it settles into a deterministic phase. But when that deterministic phase emerges is random, because you don't know when these fluctuations are going to settle down. And here we see that the variance is, the relative variance decreases. So measuring stochastic neutrons, stochastic populations is key. And there have been very many sophisticated measurement techniques that have been developed and used and implemented. I'm not an experimentalist, but I recognize that modeling and simulation plays an important complementary role to the experiments. Of course, we always have to make sure our theories and models are able to successfully predict experimental model and predict experimental configurations. So there are three main approaches to modeling, all of them sort of representing a balance between the amount of computational time and the amount of information that you'd like to attain. Of course, at the highest fidelity are Monte Carlo methods, codes like MCNP, but they tend to be computationally expensive, of course, but they give you the entire neutron multiplicity or count distributions under very general conditions, accounts for the geometry, accounts for all the interactions, accounts for all the neutron phase dependence. At the other extreme are these low-order statistical models that compute the low-order statistical moments. As we'll see, we can write down equations directly for these moments, i.e. the mean, which we're all very familiar with from the transfer equation, but you can also write down equations for the second moment, the third, and the fourth, and so on. And the existing deterministic transport codes can all be adapted to compute these higher moments. That's been done. That's quite common. Under simplified conditions, you can extract gross sample properties from these moments, especially the mass, the composition, multiplication through these Feynman Y function and Rossi alpha functions, which allow you to then connect to experiments as well, because these can be measured experimentally. So again, I'm not an experimentalist, so my ability to explain experimental configurations and experimental techniques is very limited. The third approach, which is somewhat intermediate, and what's going to be the topic of this talk is what are called master equation methods. Here we exploit the fact that the stochastic population evolves in a Markovian way, and that allows us to write down explicitly equations, deterministic equations for the probability distribution of the neutron number. Remember, the mean and so on are not adequate in this case, and so we'd like to have the entire probability distribution if possible. But it turns out that that too has its limitations. Depending on the extent of neutron branching that occurs, it can become computationally expensive. So what we're going to show here is a unique unique combination of low order statistical moment information, which is easy to compute, and low order count probabilities, which are also cheap to compute, can collectively give you an efficient method to reconstruct neutron multiplicity distributions. Okay. Very quickly, before I get started, just to point out that there is a vast history of Markov process-based modeling. It goes back the earliest time this statistical question was posed concerning populations was the extinction of surnames, and where British royalty were concerned about disappearing surnames because of which were transmitted through just the male heirs. Epidemics, of course, especially in today's world, there is a vast application of stochastic modeling. Species extinction, stock market volatility. You're all familiar with what happens on a daily basis, but you've got the noise of daily trading that's superimposed on which are kind of these market crashes that we're all familiar with. For neutrons, the early work in this area was done it's pretty much in the Manhattan Project time at Los Alamos by Ulam and Feynman. They were the first to raise concerns about potential safety implications of stochastic conditions. A general framework was developed by Pál in Hungary in 1958, but what we call the modern theory of stochastic neutron transport was developed by Bell, also at Los Alamos in the mid-60s. So in order to model stochastic systems, we need to have some definitions. All right, so let's start with a few here. We talk about a system state, which is defined here as describing at any given time t, there are a number of neutrons, the number of precursors, number of photons, number of detector counts, any quantity that is stochastic and discrete, that is a result of these fundamental interactions, fission and so on. Then that's the state of the system, that the number of these discrete objects at that time t. The system is stochastic if its future state cannot be uniquely determined from its current state, right? It's not a deterministic system, where if you know the initial conditions or if you know the state at any time, you can uniquely compute it for all future times. A Markov process is one where the future state, although not uniquely determined, depends only on the current state. In other words, the time history of how it got to the current state is irrelevant. So the key quantity that describes such a process, a Markov stochastic point process, is a conditional probability. That is that it's the probability of finding, say, n neutrons, m precursors, k photons, L counts at time t, conditioned on there being some number at an earlier time s. Okay, that's going to be our key quantity. This conditional probability evolves as a result of certain what we call mutually exclusive or disjoint events, such as death by through capture, that's parasitic capture, emigration, which is a leakage of neutrons from the system, immigration of source, that's again spontaneous fission or just background neutrons, cosmic ray neutrons, reproduction, which is just induced fission, N2N reactions and so on, and transformations, which is precursor decay, which results in fission fragments producing delayed neutrons and so on. Each one of these fundamental processes are characterized by a transition probability that gives you the probability of a change in state in an incremental time, and with the finally with the assumption that each neutron acts independently of any other neutron. right? The state that how one neutron changes a state is independent of how any other neutron changes a state. Collectively, then these outcomes can be used to determine the evolution of this conditional probability. So just to talk briefly about these so-called transition probabilities, here are the rates. These are essentially the rates for single neutron interaction. So lambda A times dt, for example, is the probability of a neutron loss by either capture, leakage, or fission in a short time dt, right? So you can almost immediately relate that to cross sections. It's actually, in the simplest level, it's V times the appropriate macroscopic cross section. S times dt is the probability of a source event. S is the source strength, right? Number of neutrons being emitted in a spontaneous fission event times dt is that. There is also the possibility that nothing happens in that short time. So we have this probability of this null event, which is 1 minus the probability of all the other events. So this is for a single neutron. And of course, we have to define our fission induced fission multiplicities. P nu is the probability that new neutrons anywhere between 0 and nu max, which this is about 8 to 10, are released in induced fission, and in the case of a spontaneous fission, we refer to that multiplicity as Q. And here we're going to ignore delayed neutrons. So that's for a single neutron, but conditioned on there being n neutrons in the system at any given time t, right? Then we construct this probability table of how the state changes. So for example, if you have a loss, then if a single neutron is captured with probability lambda c dt, but there are n neutrons, any one of them can be captured, then the probability of a loss is n times lambda c dt. So you see, this probability depends on the neutron state, and the state changes from n to n minus 1. One neutron is gone. If it's fission, then you have this probability n lambda f dt of any one of the neutrons causing fission times the probability that new neutrons were emitted, and that changes the state to n plus nu. And I should say it should be minus 1 here, because it can also, the original neutron is lost. And likewise with the source, and then the null event, okay? So these are the fundamental probabilities that need to be defined, and this is essentially all nuclear data. But what I'm going to do here is primarily talk about point kinetic models, although I will present more general results. And in point geometry, what we use standard adjoint weighted transport calculations to define these parameters through leakage rates, production rates, and so on. So the assumption here is that all of this data here is known, and we just proceed to work with it. We know one thing we can do if we know the data is to simulate it by Monte Carlo. We know that, and we can use standard single event Monte Carlo, such as MCNP and other codes. You can write point kinetic codes, but in the point geometry, a particular Monte Carlo method known as kinetic Monte Carlo method can be particularly efficient. This is known as the stochastic simulation algorithm, and it was developed in the context of chemical reactions by Gillespie. It's often known as the Gillespie algorithm. So it basically updates the state of the system the entire state of the system at each randomly sampled interaction time, right? Here's the algorithm that Jawad put together and implemented. So we start with some initial state, which is 0 everywhere, and you determine the time to the next event, and the event is any collision, and at that point you determine from a CDF of all those fundamental probabilities that we saw on the previous slide, which event occurs. Is it a source emission? Is it a capture? Is it fission? Is it a production? Is it a production of a photon? We may be tracking total number of fissions and so on. And once you've determined that, you update your time and you change the entire state. Your state now goes from this primed state to this state. So the entire state is changed at a single time. We don't have to keep track of the number of neutrons emitted as we do in single event Monte Carlo, and then store them and work through that. So this is particularly efficient, and we're going to use this simulation algorithm to define our benchmarks for these problems. So here are some SSA numerical results. This is that distribution I showed you earlier, the figure I showed you earlier was obtained using SSA. There's your spontaneous fission. This is a single fission event, single spontaneous fission event. Look at the neutrons that came out, how they multiply, and looking at the distribution of neutrons that emerged for different masses, right? You see as the mass increases, the number of induced fission reaction interactions increases, and the distribution looks quite different from spontaneous event. This is the distribution of photons for the same masses. Okay. And for an actual simulation, we try to use experimental concepts as much as we can. And a key thing in detection is the concept of time gate detection, where you measure neutrons in fixed time gates. And here we've looked at the problem where we, for the 2680 gram sample, then we had a 15 microsecond time gate. What is the distribution of neutrons that you see and photons? And this is the result. Okay, so these are relatively large numbers of counts. In this case, it's a strongly relatively strong source, and time gate is also it's not that small, but it's not that big either. So we have this ability using SSA to compute what we regard as the accurate distributions, probability distributions. Now, these are probability distributions. These are not averages. So it's still very expensive. You have to run a lot of histories, as it were. A lot of events have to be simulated to make sure that the standard deviation is low, and it generally tends to be a problem out in the tails over here. So it's one of the problems that Monte Carlo has is convergence of the statistical convergence in the tails is slow, and traditional code for applications, especially for reactor applications, we use variance reduction techniques to speed things up. But here we cannot use variance reduction. We need to have the actual analog distributions. All right. So that's Monte Carlo. And we said it's slow. So we want to develop models for that. So in addition to moments, we would like to have a model that actually gives us these conditional probabilities that we talked about. So one simplification that results because of the Markov nature of the event of the stochastic process we're looking at is that the entire neutron state over time, so these are different times, and these are the resulting neutron populations that occur at that time, can be obtained from just the 2-point conditional probability. If we know the probability, given the probability that there are a certain number of neutrons at a certain time, then we can compute the number of neutrons at the next time. And by compounding those probabilities this way, we can get the entire set. So this is the powerful feature of the Markov process. If it wasn't Markovian, we couldn't do any of this. And the other main result is that this 2-point conditional probability satisfies what's called a Chapman-Kolmogorov equation. Basically, it says that the probability of transitioning from some state M at some time S to a state N at some time T. So again, N, M, M, just think of them as just neutron numbers, is the probability of first transitioning to an intermediate stage and then summing up over all possible intermediate stages. Okay, so in this case, it's probability of going from M to N prime at intermediate time U, and then from N prime to N, from intermediate time U to the final time T. Okay. The problem with this is it's just a mathematical expression. It's a nonlinear, what's called functional equation. There's no physics in this, in the Chapman-Kolmogorov equation. Okay, it's basically just a statement of consistency of probabilities and combined with the Markov assumption. It's very easy to derive this from just without any physics at all. All right. However, we can introduce physics into the Chapman-Kolmogorov equation and make it useful. If we regard the intermediate time, this intermediate time as being incrementally close to either the initial time or the final time. Because then, for example, if U is T minus delta T or U is S plus delta S, or then you can use the conditional probability simply becomes the transition probability. And we know what those are. We saw those previously. So if we do that, and this is where you'll just have to follow the math a little bit, but the final result is what we care about. So if we condition on what's called the first source step, if we have this is the time, the initial time, we use the intermediate time as delta away from the initial source time, then the expression becomes something like this. The intermediate time is now s minus delta s. And so this is the probability that the neutron, if there were m neutrons at s minus delta s, the probability that there will be s neutrons, m prime neutrons at s. And that's just given by these transition probabilities, right? They're all independent and mutually exclusive events. So you add up the probabilities. So if there are m neutrons at s minus delta s, then in a short time interval delta s, you have a probability of neutrons being lost by capture or leakage, in which case the number is now one less, and so on. If it's fission, you lose one and you gain nu, and if it's source, you gain nu, and then there's a possibility that nothing happens. If you take this expression, stick it in here, and simplify, take the limit as delta s goes to 0, you recover what's known as the backward mastery equation. So what I'm going to do is, instead of continuing along in this general way, I'm going to now specialize and say that we're going to include neutron leakage and consider the state space to be just the total number of counts, the cumulative number of counts in the single interval. We could forget about neutrons in the system, forget about photons and the like. Okay, under those conditions, then we define this probability that given one neutron at an initial time s, that at some later time, that there will be n neutrons in this time gate between Tmin and Tmax centered around some time. Okay, and so the process gives you Chapman-Kolmogorov equation reduces to this so-called mastery equation, and it turns out that you need to write this in, you need to isolate the 0 count probability equation, and that turns out to be nonlinear. It's all because of the results of all the branching process. So we have this point kinetic equation that has this nonlinear term, but for all other count numbers, you have this linear equation that depends on all previous counts. So there are these complicated terms here, these I, K, nus, which satisfy this recurrence relation. You can see that they depend on that 0 count probability. They depend on all the previous count numbers. So if you're looking at the kth case, then it will depend on all the probabilities less than or equal to k minus 1. I show this not so much just to impress you with the math, but to point out that this is a source of difficulty. These are very convoluted algebraic expressions. They arise because of neutron branching. Okay, the fact that you can have 8 neutrons being emitted or 3 neutrons. And this becomes a computational problem because as you look for more and more, as the counts get higher and higher, then the number of terms in these expressions get larger and larger. They're easy to compute, each one of them, but they become problematic. Now here I was just talking about a single initial neutron, but of course we have spontaneous fission, and we want to see the cumulative effect of all fissions. And so for that, we need to introduce an auxiliary equation, which is an auxiliary probability, which is the probability that n counts are registered in that time, conditioned on a source being first turned on at an earlier time s. You always have to have some initial time in your problem, and in this case, we defined initial time as sometime that the source was turned on. In practice, we let that go to the infinite past. So that we can get all possible contributions to that time interval. Okay, so again, in this case, the source, so it's sort of like a Green's function in a way. The probability for the source, for the neutron population with the source, depends on the probability for the single count from these i's. The i's depend on the p's for the single neutron case. In any case, these are now the beauty about this is these are all coupled differential equations. There's some nonlinearity to them, and we can solve them numerically. As Jawad has done that, and he's produced these results. So if we just look at quickly at our plutonium sample and look at those different mass ranges. This is the probability of there being 0 counts. This is interesting. So for if the sample is large enough, the probability that you won't see any counts is will be large. Initially for very, very short times, but then because of the amount of multiplication, it very rapidly drops to 0, right? But as the multiplication decreases, as the mass of the sample decreases, then you're going to see increasing probability of not seeing any counts. And so this sort of will tell you if you have your time gate, for example, here in this region over here, you can see it'll be very sensitively dependent on the 0 count probability sensitively depends on the amount of material there. So we solve those equations, including from 0 to some number where the probability had dropped off. Adaptively, Jawad implemented this Runge-Kutta backward time integration scheme because it's a backward equation. You start with some final state and you integrate backwards. And we compared the solutions to our SSA algorithm. The SSA itself was converged to a 1% standard deviation in the low counts, but in the tails we went up to about 5%. And here you see the distribution. The blue crosses are the SSA solution, and the orange ones are the exact solution, i.e., obtained deterministically. And you can see its agreement is excellent. The problem, though, as we see, is look at the runtimes. The runtime is reasonable for as long as the count numbers are low, but as count numbers increase, and not even much, this is hardly much of number of neutrons, the runtimes start get very large. And this is the result of that expression swell that I talked to you about. The number of terms, because of the branching, gets larger and larger. They grow explosively, and that slows it down. It's not because of the number of equations, it's the number of terms in the equation. You can use some clever computer science techniques to try and minimize that, but there is a limit to how far you can go. So what we've shown here is then that as long as the count numbers are low, these direct solves is possible. Now, similarly, we can develop equations for these moments. These are known as factorial moments. These are for example, the first factorial moment is just the mean number of neutrons, and then the second factorial is related to the mean square and the mean, and from which you can get the variance and so on. And you can develop similar equations for these moments. These equations can be solved. They're linear. They have the same problem. You've got this coupling through the previous moments, but up to about 5 or 6 moments, these are relatively easy to solve, and some of them sometimes you can solve them analytically. And so those analytical solutions can be used to develop these gross sample properties in a sort of in a inverse way, but it's not very practical for realistic problems. But key thing to observe is that these low order counts and the low order moments and the low order count probabilities are relatively cheap to compute. So can we combine them collectively and obtain a more effective, develop a more effective way of obtaining the complete distribution? The answer is yes. There are 2 ways we want to look at now. One is what's based on an orthogonal polynomial representation that uses this information, low order information, and another one based on maximum entropy. So the approach, the orthogonal polynomial approach is to identify such a polynomial whose weight function is already a valid probability distribution, right? So if you're familiar with Gaussians, then a distribution that's a weight function for the Hermite polynomials and so on. In this case, we found that the gamma distribution, which is given here, so it's basically n8 out of the n raised to some power times e to the minus n, which has got 2 parameters. You can actually capture the mean and the variance exactly, right? That's low order information, but that's actually in itself a pretty decent distribution for count numbers when the count numbers are large, as we'll see. So to generalize that, we've recognized that the gamma function is the weight function for a generalized Laguerre polynomial, and so we can do this generalized Laguerre representation and use orthogonality and a knowledge of the higher moments to obtain these expansion coefficients, right? So here's our distribution. So we have a truncated distribution. Lowest order, it's a gamma, and that can preserve 2 moments. But then by keeping the higher order terms here, we can preserve more moments. Okay. So the question then is, how good is this distribution? Important to note that by replacing the discrete distribution, we've replaced the discrete distribution by a continuous one, and this is justified if n is reasonably large. So here's some results. So here we have the blue dots, the crosses there are the SSA, and here we've got the oranges, just the gamma distribution itself. This is for the 335 sample with a reasonably large time gate. But as we add more moments, up to about 6 moments, we see that the distribution gets closer to the experimental or the Monte Carlo simulated result, but never quite close enough. If we go to a larger source in a smaller time gate, just to keep the counts small enough, you can see again that the convergence to the SSA is pretty quick. So you need about 4 or 5 moments, and it gets pretty close. However, and so now if you go to a very large sample, a very large count numbers, this is times 10 to the 5, right? 40,000 counts. It turns out just the gamma distribution alone can do a pretty good job. That's the orange in capturing it. The blue is just 1 more moment. So this is very efficiently done for very large count numbers. Okay. On the other hand, though, when you go to a situation where the low count, the 0 count probability, this is as I say, the 0 count probability is high, then these fits do a poor job in this region over here. Okay, so that's where this approach fails. You will need very large number of moments to recover this non-monotonic behavior. So then we looked at something called maximum information entropy to use as a fit. In this case, so the entropy of any distribution, or the Shannon entropy or information entropy, is defined by this nonlinear expression of p log p summed over all states. And we construct this distribution by maximizing this entropy subject to some constraints, and the constraints are these moments. So don't worry too much about the math, but if you're not familiar with this, but typically we define this modified entropy functional, which is the original entropy functional, constrained by these moments, right? So mu k are the exact moments that we know, up to about say 5. And we introduce these constraints through Lagrange multipliers, and we can maximize this modified functional with respect to these approximate probabilities and the Lagrange multipliers. That gives us a nonlinear system. It's very nonlinear. Remember, this is an exponential, and we want to compute these lambda k's given the moments. And if you can compute those lambda k's, you can reconstruct this distribution. This is the maximum entropy distribution as a function of n, right, with respect to all this. So there's a lot that goes in. Jawad had to work very hard at getting this work to work efficiently numerically, which is why we went to this so-called, what are called normalized central moments, as opposed to just the raw moments. And here are the results for the same 2 samples that we looked at before: 335 gram sample of plutonium, and then again the other one where the 0 count probability is high, and you see relatively similar performances. It's as good as the Laguerre construction, really, in terms of accuracy. So in other words, wherever the max end distribution is comparable to the Laguerre reconstruction, wherever the latter is accurate, which is here in this case, for example. But also, like the Laguerre, the max end fails to capture key features, right, resulting as a result of a significant 0 count probability. All right, so in this case, we notice that that the problem arises at the lower counts, right? It's not in the tails, but if you remember what I said earlier, the lower counts can be computed exactly very easily, quite cheaply, and also the moments can be computed. So the question then is, how can we exploit this information, additional information? Well, it's quite easy in maxent. We can modify the constraints to incorporate some exact low count probabilities. And so that's given here. And so we take the first n star counts and compute the probabilities exactly. Let's assume they're given, and then constrain the others by what that additional finite amount of information, which includes count as well as moments. And so the modified result is then, I got to keep track of time here, sorry. Modified distribution is given here. So for the first n star count, you recover the exact distribution by definition, and the rest of the fit, the rest of the distribution is given then by the max n fit. How does that work? Well, very well. So here's the case where you can't really see it, but I'll talk about the errors in a minute. Again, so this is the orange result is the max n result with just 5 moments. And the other results, the green results, or the max are the moments plus 5 or 6, I should say, including the 0 count discrete probabilities. And the distribution is very, very close, which is 6. In this problem, using in this way where we had this feature, this non-monotonic feature appear, we noticed that with 6, the distribution, so we've got first 0 to 5 exactly done. But if those are the only ones we preserve, then you see this kink before it then settles down and gives you a very accurate fit in the tails. But if you include up to 10, you cannot see the difference. The discontinuity will shift up at 10, and you can see a slight kink over there. Actually, that's but it's significantly less than that. Okay, and so it sort of appears, and I use this word loosely, that sort of an optimal reconstruction can be achieved with 5 moments and around 10 discrete probabilities. So convergence, how accurate is that, and how do we define that? So for these are probability distributions, and so I'm sort of talking about least squares and so on. It turns out that there are other measures that are used in statistics to define closeness or proximity of 2 probability distributions. One is sort of an entropy-based method, which is this KL or Kullback-Leibler divergence. Given 2 discrete distributions Pn and Qn, the divergence of Qn to Pn is then defined in this entropic way. Pn in this case, our case, would be the SSA, and Qn would be the approximate. Written this way, you can sort of see an information entropy interpretation. Since this is the entropy or the information content of that distribution, then this piece over here, the result of using Qn represents the information that's lost when you approximate Pn by Qn. It is important to note that this is not a symmetric measure, so it's not really what's called a distance measure. But another measure is the Hellinger distance. It's also defined for 2 discrete distributions, defined this way. It is symmetric, and it can if that matters. But the important point is in both of these cases, they measure, the closer Q gets to P, the smaller the result, the distance or the divergence will be. So let's look at them. So for the case of this 2680 grams sample, where we just looked at the Laguerre polynomial reconstruction, if we have 2 moments, here's the Hellinger distance. At 3 moments, it goes down, and so on. And at around 6 moments, we see that there is some trouble, that it seems to be rebounding. Similarly, with the KL divergence, we see a reduction, but mostly a saturation. So for just moment-based reconstructions using orthogonal polynomials, we see low but not strongly decreasing convergence. On the other hand, with maximum entropy, where we have both moments and discrete probabilities, we see that we see a different result. We see that for any given, so in this case, the blue curve here is for if you keep 2 moments, and on the x-axis are the number of discrete probabilities retained. Remember, we're going up to about 10 or 11. We see that the error of these measures, these distances or the divergences, decrease very sharply with increasing number of discrete information that's preserved. And this is, for this problem, it's that complicated problem where we had the features where the corresponding to the significant 0 count probability, right? And so we see a more significant a decrease in error as a result of including these discrete distributions. And what we see, of course, is by the time you're at the sixth moment, it actually it seems to get worse. And we've noticed that this is more a consequence of the maximum entropy process. In this case, we still need to the fits are in both cases it's the maximum entropy algorithm. There are some the more moments you preserve, sometimes it can be hard to converge and find a solution. So we regard up to about 5 moments as our very reliable limit. And there you can see that if you look at 5 moments and 10 discrete probabilities, in both cases the distances are small. So okay. I want to quickly move on because I'm running out of time. Actually, how much time do I have, Jason?
So we typically take questions soon. We've got until 2:30 local.
Oh, so I should stop very soon now. But I just wanted to quickly, I'll just go over this. I want to show you that these reconstruction algorithms are agnostic to how the low order stochastic information is generated. In other words, you can obtain these moments using very sophisticated simulations based on, say, MCNP, and you can take into account all the geometry and nuclear interactions and phase dependence, and we can then also establish the accuracy of our reconstruction algorithm. So very recently, Jawad, working with Jess and Hutchinson at Los Alamos, started applying these to a benchmark experiment there. It's called the SCRAP experimental confirmation. This is a subcritical copper reflected alpha phase. Just to quickly show you, I'm not an experimentalist, so don't ask me too many questions. But basically, it's what's called the burp ball without the beryllium around it. It's a stainless steel clad alpha phase plutonium metal sphere, which is right there, and it's surrounded by 2 detectors. They consider both bare metal sphere configurations as well as metal spheres with their polyethylene reflector. And we're going to look at one particular scenario where there was a 4-inch reflector. And so Jawad was able to, the benchmark solutions have already been provided in MCNP. Jawad was able to reproduce them and extend them. And we looked at the maximum entropy reconstruction of those. And here are the results. So in one case, for a time gate of, this is a large time gate, 2048 microseconds, we see that the fit with just 3 moments, 3 and 4 moments, here you can see 4 moments is adequate. For the case of the bare sphere, for the reflected spheres also. Maybe it needs more. The blue crosses are the MCNP data, and the other results, the others are the max end fits. But when Jawad ran a smaller time gate problem, we recovered this non-monotonic feature, and in that case we had to include also the discrete probabilities. But again, you only needed about three moments and about 3 discrete probabilities, and it does a very good job of reproducing the entire distribution from MCNP. So we think very efficient reconstruction is feasible with very low order statistical information. Okay, so I'm gonna have to just leave this now but we are now extending this to include, to develop our backward master equation formalism. I mean, MCNP is still a very expensive prospect to run to get what's called list mode data, compute moments, and so on, and converge in the tail. So what we want is to generalize our master equation to give you a much more meaningful probability that also includes phase space effects. We've done that, and I'm going to skip that. I'm sorry, don't have time for that. But we've looked at, just to show you, here are some single chain distributions in the Lennell sphere and in the burp ball, the result of putting a neutron at different places in the sphere at different times. And here we see spectral effects. Here we have some fast group and we have thermal group work. This thermal groups over here. This was work done by another student of mine at some years ago at Imperial College. We were just looking at internal distributions. What Jawad is doing is now generalizing that to look at external distributions. So quickly, just to summarize then, what we've shown is that you can develop these deterministic approaches to actually compute multiplicity distributions, neutron multiplicity distributions, and also photon multiplicity distributions. And by combining low order statistical information from moments as well as the actual probabilities, you can get a very efficient reconstruction. We've demonstrated that for point geometries, but also shown that the algorithm works well for any model, any fidelity model. And we're currently generalizing this to the approach of the deterministic approach. We're going to assess the accuracy of point geometry distributions, right, compared to the exact ones, compared with a representation that accounts for finite size and neutron phase dependence. And we also want to develop more general reduced order models. Point kinetic models are known as reduced order models, and the one we're familiar with is the simplest. Can we generalize that? And so we're also looking at that. Finally, I just want to comment that this master equation formulation, which we've shown is a powerful alternative to Monte Carlo simulation. It has relevance beyond just nonproliferation. For example, it enables us to study phenomena exactly at critical. There's a very interesting behavior of neutron chains that can be investigated, looking through this probability of distribution of chain extinction times. And also we're interested in going beyond neutron numbers, looking at the stochastic distribution of, say, deposited fission energy with towards the red. So with that, I'll stop. I'm sorry if I ran over, and I'll be happy to take some questions.
So thank you very much for your presentation. There were a couple questions that came up during the presentation in the chat. So Dr. Upadhyaya said, and this is back at 147, so I have no idea what slide. But he said, are the higher moments computed numerically with the knowledge of the underlying probability distributions?
The higher moments are, yes. So the higher moments are computed from the moment equations themselves. That's the beauty about it, right? I showed over here that using that from this definition, the moments these are called factorial moments. These are averages of the probability distribution. We already obtained the equations for the probability distribution, so we can transform them to equations for the moments. So we actually are explicitly solve for the moment equations and use that information in the reconstruction.
Okay, the other question was asked, did you see any needs to improve the nuclear data you've been using for your model?
That's the key question, isn't it? It's the cop out for me is to say that's beyond the scope of my
Yeah, it's beyond it. But do you think it's is it a need?
Absolutely.
For the work you're doing?
I think
yeah, because the Monte Carlo calculations are all using the nuclear data, and if the nuclear data is uncertain, then you have uncertainty in the Monte Carlo, and if you're trying to get something to match that, you're matching it to something that you don't know if you're matching it to the right thing.
You're absolutely right.
Right.
You're absolutely right. That's uncertainty quantification is another layer on top of this that you would have to do. And work is and people have done work on that. Los Alamos has done a lot of work on propagating uncertainties through these moments, and then of course how does that affect what you learn about the sample through this through the sample mass composition, things like that. You're right. Absolutely right.
Okay. Another question says, I'm interested to hear more about how you plan to incorporate external reflection and non-point geometries. I know you skipped over it due to time, but any chance you can talk slightly more about it?
Very good. That brings me, it's going to be so we have to come to this. This is the formalism you have to go to. I'm sorry, these are just a bunch. I'm just flashing up equations here. That doesn't work. I'll be happy to talk to you after. If you contact me, I'll be happy to talk to you separately and show you the derivations. Yes, you have to introduce. This is done through boundary conditions, and it's through. We're not going to actually have reflecting conditions. We're going to. The idea is to do the computation throughout the region and look at the counts, look at the distribution of neutrons leaving the system now. And the assumption is that I'm not focused on the detector. I'm assuming every neutron comes out is detected. That's a separate problem. But we are able to compute the distribution of neutrons leaving the system, accounting for all the different materials and interactions in there. Yeah. But if you're specifically interested in having reflection included in there, that can be done as well through the right kind of probability counting, right, in the balance equation. I'll be happy to, if you get in touch with me, I'll be happy to talk to you.
So we're basically out of time, but do we have any other questions? The student said he'll get a hold of you outside of this.
Okay.
Uh-oh, Dr. Upadhyay is videoing in.
Thank you.
Okay. Says, anybody have any other questions? Jason, did you have any questions?
No, I think it was captured by Aaron's question. Thanks so much for coming.
Oh,
Yeah, thanks so much for sharing your expertise with us, and best of luck in your failed retirement. Because if you're really retired, you wouldn't be doing all this work.
Flunked retirement, yes.
But I know that's what drives you and that you love this. So thank you so much. It was great seeing you again. Great having a chance to talk to you before we got started, and have a fabulous day.
You too. Thanks very much. Thanks.
Bye-bye.
Bye. I hope to see you soon sometime. Bye.